Hello, calculus students. This is Mr. Beck. Today we're going to be continuing our discussion of sequences and series, but first let's talk about a recap of where we've been. In 7.7, we discussed the L'Hopital's rule, and we discussed when we had two functions, the rate of change at which each function approached that certain x value that we were concerned about was the actual limit itself. We're going to be bringing some of that back. In 7.8, we took improper integrals, and with improper integrals, we took the integral to infinity. We're going to see a little bit of that as well. 8.1 was kind of like a pre-calculus reintroduction to sequences. And then in 8.2, we discussed, okay, what happens when we add the terms of the sequence? We now have a series. And when we have a series, we want to know, are we going to be able to find the sum of that sequence, or the sum of the terms of the series, or is it going to be indeterminate? And that's where our big discussion is about, does a sequence or does a series converge or does it diverge? If a sequence converges, then we're able to find the sum. If the sequence diverges, we're not able to find the sum. So without further ado, in 8.2, some of the tests that we talked about to determine if we have convergence or divergence. The first one is the nth term test. And with the nth term test, what that says is the limit as n approaches infinity of the rule has to be 0 in order, for convergence. So for convergence. Now, we're not guaranteed convergence, but it's for convergence. If the limit as n approaches infinity of a sub n is not equal to 0, it diverges. So that's going to be our very first quick check to see if a series diverges. It's that nth term test. The second test that we talked about in 8.2 was the geometric series. And if you remember with a geometric series, what's going to occur is if the absolute value of the ratio is less than 1, officially greater than 0 as well. So if the absolute value of the ratio is less than 1, then we have convergence of the geometric series. And if it's greater than 1, we have divergence. One of the problems that I'd like to stress, because we're going to bring it back later on in this chapter, we had a problem in the homework, or a series of problems in the homework, where we said n equals 1 to infinity. If we had, that's a bad infinity, let's try to redraw that. So if we had that of, say, x minus 4 over 7 to the nth power, what causes convergence? What x values cause convergence? So for what x do we have convergence? The absolute value of x minus 4 over 7 has to be less than 1. So what we could do is we could say 1 is less than the absolute value of x minus 4 over 7. And we don't need the absolute values anymore, so let me get rid of those. So negative 1 is less than that, which is less than 1. So negative 7 less than x minus 4. I keep wanting to put those absolute values in there, and they shouldn't be there. Less than 7. So now when we add 4 to all three parts, we have negative 3 less than x is less than 11. So the values of x that allow for convergence are going to be all the values from negative 3 to 11. And we'll have some more meaning for that as time goes on. But I wanted to make sure I talked about a problem like that, because this is geometric sequences. For geometric sequences, it's going to be true. So anyway, let's keep going. Next, what we have is what we call the integral test. Now, to set up the integral test, I do have a link on the notes, and the link is to this GeoGebra site. So when it comes to the integral, or when we want to know or look further at whether a function or a series converges or diverges, let's talk about the series. The series right here is represented, each term in the sequence or in the series is represented by this rectangle. So the first term has a value, a base of 1, second term has a value base of 2. If we take a look at the function that creates the series rule, then if we look at this function, say, okay, the first term is going to be the height of that function, basically turning our numerical approach into a graphical approach. What you'll see right here is the height of each one of these rectangles ends up being the function value. So we're turning the series into a Riemann sum, if you will. And this one's going to be a right-hand Riemann sum, as what we see here. Now, if we look at the function itself and we find the integral of this function is going to be the area underneath the curve. And we if we want to, let me find a good way of saying this. If we want to know if the series is going to converge, what we could do is we could use the integral to help us determine if that series is indeed going to converge. So the integral from 1 to infinity, I'm going to exclude this first term temporarily. The integral from 1 to infinity is going to be the area under this curve. Since that integral ends up being a larger value than the series itself, then we could use the integral to say, okay, if the integral converges, then the series, which is smaller, will also converge. So let me say that one more time, that the integral from 1 to infinity, that area under the curve is going to be a representation of the series itself. And so the sum of all those terms is going to be smaller than the integral value. Since the sum of all these terms is smaller than the integral value, what's going to happen is if the integral converges, then the series itself is going to converge as well. So going back to our notes, that's what I'm going to talk about. If we have a function where, if we have a series, the integral or the sum from n equals 1 to n equals infinity of 1 over 3n plus 1, if we want to determine the convergence or divergence of this, what we could do is we could use the integral of the rule. You can call this f of x, you can call this f of n, as long as your variables match up or your differential matches up. What you can see is I took the integral, and again, this is an improper integral, so this is 7.8 coming back to work with us. I found the actual integral, and that was infinity. So because the integral diverges, the series, which is smaller than the value of the integral, will also diverge as well. Now, is this going to be true for everything? No, it's not going to be true for everything. So we do have some conditions that we need to talk about for our integral test. Number one, our rule has to be positive, because what happens if our function goes below the x-axis, then we have some areas that are positive, some areas that give negative values, and our integral is not really conclusive anymore. So this is only going to be true for positive series. Number two, our series must be continuous, or at least the function itself has to be continuous, because the function is going to be a representation, a geometric representation of that series. And so a discontinuous function will mean that we have a discontinuous series, which doesn't really make sense. Third and foremost, we must have a decreasing function. So it's a positive decreasing function. Now, part of the reason for that decreasing is what happens if we have an increasing function that's modeling the series. Well, that's really by the nth term test. By the nth term test, that's going to be a divergent series anyway. So we're only going to do this integral test for a decreasing series. All right. Now, as I said, that integral, because the integral ends up being a positive value or a bigger value than the series, if the integral converges, then the series will converge. But what I didn't talk about is what happens if the integral diverges. Well, if the integral diverges, then the series itself is going to diverge as well. And the reason for that is because if we shift over that series, what we can see is now the integral is going to be smaller than the value of the series. So if the integral itself diverges, then the series is going to diverge as well. So in the first case, I took out that first term because in essence, we can figure out what happens with the rest of the series, not based off that first term. But in terms of the integral, if the integral diverges, then the function itself is going to diverge, or the series itself is going to diverge. And honestly, this is a case that if we have 1 over the square root of x, if we take the integral from 1 to infinity, that itself is infinity. I could write this down on my other screen, which might as well do that. So on my other screen, let me zoom in here. And if I said, what is the integral from 1 to infinity of 1 over the square root of x dx? This is the limit as b approaches infinity of x, the integral from 1 to b, x to the negative 1/2 dx. So that's the limit as b approaches infinity of 2x to the 1/2 from 1 to b, which is really infinity. Because that limit is infinity, then we know that we have divergence. So going back to this graph, because the integral diverges, the series, if I had shifted it over one term, we could see that, that series is now going to be greater than the value of the integral, so that series will diverge as well. So the two are linked together, the integral and the series. So that integral test ends up being powerful, as you saw that I did that first example. Second example, we should check, and we should always check, is this a positive series? Every term in here is positive. Is this decreasing? How do I determine if that's a decreasing series? One approach that I could take is I could start plugging in numbers, and I can see visually that that's what's going on. Another approach that I could take is sort of like a L'Hopital's rule approach, that if the derivative of the numerator is smaller than the derivative of the denominator, that means that the numerator is increasing at a slower rate than the denominator, and therefore we should have a decreasing series because the denominator is getting bigger faster. But then we have continuity that we should check for, and we do. So what I did was, this is a problem that's kind of naturally set up. We could do the integral test. If you notice, the numerator is a derivative of the denominator right there, or at least the u substitution that we could do. So you can see that I did the integral test, did my u substitution. Don't forget to change your limits. And in doing so, I now have the limit as b approaches infinity, -1/2 u to the 1/2. When I plug in infinity, or find the limit is what I probably should say, I end up with 1/72. Because I do have a distinct value for my limit, the series, or the integral converges, therefore the series converges. And it's always going to be important that you explain why that convergence is due to the integral test. Now, the integral value is 1/72, but please know that the integral value is not the sum. So this is the integral value, and let me change colors on here just for representation. This is not the sum. I wish I would have chosen a color other than purple, but oh well. So that's not the sum of the series, that's just the integral. The integral converged, so therefore the series converged. Take a look at this expression. Once again, those things that we should always be checking for. Is this positive? Yes, because there are no negative terms in there. Continuous? Yes, both n and e to the n are continuous, or are continuous functions. And this is decreasing. Again, we could use a L'Hopital's rule approach. The reason why it's decreasing is e to the n gets bigger faster than n does. So it's about the rate of change at which we approach those values, or the rate of change of those functions. So anyway, if I do the integral, this is a perfect opportunity for us to refresh our skills on integration by parts. Now, the integration by parts that I did it more by the tabular method. So with the tabular method, if you remember, our u, then we take the derivative of all the u's. This is my dv, I integrate again, and it's going to be first minus the second grouping. And now when I take my limit as b approaches infinity, I will get 2/e. That limit does converge, and since the integral converges, then the sum converges by the integral test. Number 4, this one I didn't actually do, but I could do that very, very quickly. So if I take the integral from 1 to infinity of 1/n dn, that's a natural log of n, from 1 to b, where I'm taking the limit as b approaches infinity. So this is going to be the natural log of b minus the natural log of 1, which is 0. And the limit as b approaches infinity of the natural log of b is infinity itself. Therefore, we have divergence. So this diverges. And since the integral diverges, then the sum diverges by the integral test. Now, hopefully, at least one of you knows that this summation, this infinite series, is something special. It's what we call the harmonic series. I wish I could spend some time talking about the harmonic series, but this video is going to be but what this should kind of prompt us to say, okay, if we take a look at the different functions that we worked with, the first function was that we saw on the other graph was really the integral of 1 over x to the 1/2. This diverged. The integral of 1 over x, and there's some bad notation here. This is all going to infinity. That diverged as well. What converged? We had a problem that looked like 1 over x cubed dx, that converged. So what's that sweet spot for where it goes from divergence to convergence? It really involves how we take the integral. So how do we take the antiderivative? The antiderivative of this one was x to the 1/2. It's 2x to the 1/2, I know. The integral of this one was natural log of x. The integral of this one was 1 over x squared. Again, it's not exact, but it's leading to the idea of, because we're still going to have 1 over infinity, bad notation, but the idea is because we're still going to have 1 over infinity, that 1 over infinity is where we're going to get our convergence. Where this is the natural log of infinity, which diverges, infinity to the 1/2, which diverges. But the idea is whenever the denominator has an exponent bigger than 1, that's our sweet spot, which leads us to what the p-series is. The p-series just says that. So this is really just kind of it's a specific thing that we can look at, but honestly, we're going to be using this quite a bit. And this is a great justification. Now, why does it work? It has to do with all what's going on with the integral test. The integral test leads to this. But if we have the sum of 1 over n to the p, then we'll have convergence if p is greater than 1. We'll have divergence if p is between 0 and 1. Now, technically, we don't really need to have that 0 there. If p is negative, what ends up occurring is we're going to now have like the integral of, if p is negative 1, this is the integral of x to the first when we reciprocate it, which ends up diverging by the nth term test. Now, we do like to specify this only is for 0 to 1. And a lot of that has to do with when we start looking at some complex values and we start going into higher forms of mathematics, we'll be able to see some of the reasons why we say from 0 to 1. So this one right here, p is 1. Now, officially, this has a 5 as a coefficient, but the series, we can take that 5 out. So we'll diverge by the p-series where p equals 1. This problem, one of the things that students tend to sometimes have a problem with is writing this properly. That's n to the 3/5. So the sum of 1 over n to the 3/5, n equals 1 to infinity. Because p equals 3/5, that will be divergent. Then we get maximum error. When it comes to maximum error, one of the ideas, and if we go back to that graph, that we'll see is if we take the partial sum of those terms, and then we add a certain remainder. So let me go ahead and go to that screen really quickly. So if we take a partial sum, like suppose I take the sum, I guess the smallest value I can have is 11. So if I take the sum of those 11 terms, the sum of 11 terms plus the remainder, and this is where I should scoot it over, some of the 11 terms plus the remainder, that remainder is going to be smaller than, or that remainder is going to be equal to the actual sum. So the remainder is going to be, in this case, the sum plus the remainder is going to equal the overall sum. Now that remainder, and this is where I was going with it, that remainder is going to be smaller than the integral from that 11th term on. So going back, this is where I probably need to write it down more. So where the sum plus remainder is the overall sum, that remainder is going to be smaller than the integral from that nth term on. Hopefully you caught that and you saw all of that together. But anyway, if I want to find the approximation for the sum of the series, now if I do the sum of the first 4 terms, let me actually go to this graph and show you what's happening. So this is x to the 5th. So if I take a look at this graph shows a little bit of why the nth term test really, or the p-series test works. If you notice where that x, if I had this as x to the 1/2 power, then what ends up happening is the reason why it diverges is there's always a countable amount of rectangles that we're going to have. Because we always have that countable number of rectangles, we're always adding a substantial amount. Now, at some point, let me go ahead and do the 1 over x graph. We can see this is getting smaller, but this is still countable, if you will. But let's go to the problem that we care about, 1 over x to the 5th power. If you see all of these values, and it didn't really take long, but all these values after maybe the 3rd term are a bunch of nothings that we're going to be adding. And I know it's not nothing, but they're so small, they're not going to add substantial value to our estimation. So we're going to estimate the sum by taking the sum of the first 4 terms, which graphically you can see that there's not much we're going to be adding right here, but it should be a fairly good representation. So without further ado, to take the sum of the first 4 terms, plug in 1, plug in 2, plug in 3, plug in 4. That would be a non-calculator approach, but you could see on our screen, we actually do have a calculator that we could use. So let's go to our favorite button. Our favorite button is going to be right next to the bookmark, which is the catalog. And the reason why we're going to that is because we could do series in here. So let's, let me go to the problem, try that one more time. So we get our series. We could use whatever variable we want. I'm going to go n equals 1 to 4. And the rule, once again, is 1 divided by x to the 5th power. And so now let's keep our variables the same. Try that one more time. Nothing like doing this live. All right, we have that decimal value, or that fraction, which I really would like to know the decimal value for that as well, which is the 1.03634. All right. And if I want to take that decimal place further, remember, once again, you could either change the settings or you can scroll up and hit enter on that one. And you can see those are the values that I have right here. So this is an estimate of our summation. And graphically, this should be a fairly good estimate. Well, what happens if I want to know the maximum error? I will then take the integral from 4 on to figure out what that error is. You can see that I did that with my limit notation, so that remainder has to be less than or equal to 1 over 1024, which then we could say the overall sum, so the maximum amount of our sum is going to be our partial sum, so this was S sub 4, and then plus our remainder of 1 over 1024. So we know that remainder has to be smaller than the actual sum. So, which I get this value. Now, what I could do is I could say, and by the way, you could see that we are really, really close, that we are within 1/1000th just by taking the 4th partial sum. But what if 1/1000th isn't enough? What if and this isn't in your notes, but what if I want to find the smallest n value? So how many partial sums do we have to take for our remainder to be smaller than 1/100,000th? So our 1/100,000th has to be bigger than the antiderivative, which is what I found over here. So it has to be bigger than the antiderivative. And then we could say reciprocal property, solve for n. So n has to be greater than or equal to 12.57 something-ish. Well, n stands for an integer value, so n equals 13. If I had to do this without a calculator, this would be fairly obvious, or you could plug in n values until you get a number that is bigger than 100,000. This one was definitely more of a calculator problem. I know I didn't really show it to you. I'm assuming you know how to do the 4th roots on your calculator. So quick recap of where we've been. So the recap of where we've been is in 8.2, we talked about the nth term test for divergence. And then also in 8.2, we talked about geometric series. Then today, we've talked about the integral test. And the 4th thing that we talked about was p-series. So really, our first approach is, let's take a look at the nth term test, and then all of the other approaches are going to be, which one does it follow, so that we can determine what test to use. Well, the next one we're going to do is what's called the direct comparison test. Our direct comparison test is something that I've already sort of applied as I was looking at this function. So let me go back to 1 over x, or at least something that is we can see a little bit well. If you remember, I said, okay, I know that the sum of all of those terms, so the series, ends up being smaller than the value of the integral. So the series is the value of the integral. So if the integral converged, then the series itself converged because the integral is bigger. If I look at the series in this way, if the integral diverges, so if the integral diverges, then the series itself, we could write it as, or show it as being bigger than the value of the integral. So if the smaller value diverges, then the bigger value will diverge as well. Going back to the notes, I showed that here, and that's what our direct comparison test says, that if the series A is smaller than the series B, then if the bigger sum converges, then the smaller one will converge as well. Or if the smaller one diverges, the bigger one diverges. We're going to use that approach as we look at some problems. Now, if I look at problem number 7, I don't want to show all the work just yet. If you notice, I'm saying, let's do some kind of comparison to 2 over 3 to the n. So when I look at this, number 1, can I find the integral of this? The answer is probably yes, but I really don't want to. Is this geometric? No, it's not. What about the nth term test? What is the limit as n approaches infinity? That limit does equal 0. And since the limit equals 0, then it can converge, so it definitely doesn't diverge. But the limit, or the nth term test, says this limit is going to be 0, therefore it can converge. So that's what do we do? And this is the case of let's compare it to something we know. And so our comparison, as I'm showing, is this compares to 2 over 3 to the n. Why am I comparing it to 2 over 3 to the n? Primarily because 2 over 3 to the n is one of those tests that we've already done before. In fact, 2 over 3 to the n is a geometric. And if you're wondering why is that geometric, well, that's because we could write this as 2 times 1/3 to the nth power. So this is geometric in nature. It's not itself a geometric series, but it's geometric in nature, which is why we're going to compare it to a geometric series. So the geometric series that I chose to compare it to is 2 over 3 to the n. So what that means is we need a series that is bigger than what we have. And so we have to check, is 2 over 3 to the n bigger than what we have? Yes or no? I'm telling you that it is. You can see that I'm saying that it is, but how do we know? If you don't know, what you can always do is you can always plug in terms. So for this series, if I plug in n equals 1, I will get 2 over 5 plus 3, which is 1/4. If I plug in 2, I have 2 over 5 plus 9, which is 1/14. If I plug in 3, I get 2 over 5 plus 27, which is 1/7. 1/7, and then this is 1 over 16. So that's what I have. If I check 2 over 3 to the n, then 2 over 3 to the first is 2/3. 2 over 3 squared is 2/9. 2 over 3 cubed is 2/27. Can you see that what we're comparing it to is actually greater than the function that we have? So this is what we have. We need a greater one. And this greater one will converge. Why? Because of it's a geometric series. And since the greater one converges, the smaller one will converge as well by the direct comparison test. So this is kind of the proper way of showing it that, okay, let's compare it to something that we know is going to occur. And in that comparison, if we are assuming that we're going to have convergence, we have to find a bigger sum. If we're assuming that we have divergence, we have to find a smaller sum. So when I look at example number 8, I want to know, does this converge or diverge? I need to have some kind of instinct about what's going to happen here. So if I look at 2 over 1 plus the square root of n, this kind of resembles a little bit of 1 over the square root of n, which diverges. And that's what I'm showing you right here. Now, one of the cautions that I have here is 2 over the square root of n is actually greater than 2 over 1 plus the square root of n. So if we have a divergent one greater than the one we want, that doesn't tell us anything. So what I did was, let's compare it to something simple. And if you see, the simple thing is 1 plus 1/2 plus 1/3 plus 1/4. So notice that the first terms are both 1. Let's throw out the first terms and compare everything else. 1/2 is bigger than what we have, or is smaller, excuse me, than what we have here. 1/3 is smaller than what we have here. In fact, both of those numbers are just slightly less than 1. 1/4 is definitely smaller than 2/3. If we continue drawing this or writing out all these terms, we could see the 1 over n ends up being smaller. That's part of the power of the harmonic series, that it's easy to use, and it honestly is a great comparison. So it's kind of like the borderline comparison. But anyway, since 1 over n is smaller, we do have our smaller sum. And since that 1 over n diverged by the p-series, then the greater one diverged as well. And this is, I'm sorry, some bad notation. So n is 1 to infinity, summation n equals 1 to infinity. On example number 9. If I look at this, I can't integrate it. So let's compare it to something we know. And that comparison to something we know, you see I have here as e to the negative n, because then we could do an integral test on that one. Or I guess technically, we could probably do this as 1 over e to the n and look at this as a geometric series as well. But anyway, so with that geometric series, or if we do the integral test, we know that that is going to converge. So we are expecting this one to converge. So by choosing the e to the negative n, the e to the negative n is greater than, we could see that if we plug in those values for each of the terms of the series, then since the larger one converges, again by integral test, then the smaller one will also converge as well. And last but not least for today, we have what's called the limit comparison test. So the reason why we're going to, or the purpose for the limit comparison test is when I have a series like this. Okay, this is not something I want to integrate. What can I directly compare this to? I might not actually know something that I can compare this to. Because for me, I mean, while I love the numerical approach, I'm also not strongest in the numerical approach. So what am I going to do with this? I'm not going to just sit here and randomly try to come up with some functions that I'm going to compare this to. This is where what we have called the limit comparison test. The limit comparison test, once again, says if I have two series that are both positive terms, and they should be decreasing as well. It's not necessarily required as a condition, but you're not going to do a limit comparison test if the series is not decreasing. But anyway, the ratio of those limits, if those ratios equal an actual number, then the two series will both either converge or they'll both diverge at the same time. Let me give some kind of context to this. And this is where the L'Hopital's rule idea is going to kick in, that the limit of these two series, like the functions in those series, but what we want to know is if these two series change at a similar rate. Now, those don't necessarily have to change at a 1-to-1 rate. They could change at a 1-to-2 rate, but if they change in the same nature, so let's call it the same functionality nature. So the same functionality nature. By looking at these changing at a certain rate, and that rate is a number as opposed to a function, or really more as opposed to 0 or infinity, then we know what's going to happen with both series. So let's take a look at this one in more depth. If you think about large numbers for large numbers of n, what happens after the first term is essentially irrelevant, because the first term in each the numerator and denominator are going to kick in. And that's why we're going to look at the first two terms and reduce it to say 1 over n cubed. So for really large numbers, this function is similar to what happens to 1 over n cubed. And that's going to be our link. So with this 1 over n cubed, I will take the ratio of the series that we have to the 1 over n cubed, which is a sort of modeling, find that limit, multiplied by the reciprocal, and that limit ends up being 1/2. This 1/2 is a finite positive number. Actually, just a finite number. Doesn't necessarily have to be positive, though it will be on most cases. But since this limit is L, or this limit is a number, then 1/n cubed as the series converges by p series, then the function or the some series that we have also converges by that same limit by the limit comparison test. I've obviously been talking too much. So again, the idea behind this is I want to create a series that has a same rate of change as the series that I am looking for. So on this one of the things that if you have my notes, one of the things you'll notice is I am changing this. I changed that from a positive to a negative. And the reason for that is because I wanted to show something specific. Notice I still want to compare this to a 1/n squared because that's what I'm really doing. But if you notice that first term, if we write out all those terms, the first term is not positive. The first term itself is going to be negative. Let me pause these. All right, now that the announcements are over, let's continue on. What I was saying before was the first term is not a positive number. The first term now itself is negative. If we continue on all the other terms, all the other terms are going to be positive just because that bottom is quadratic in nature. So once it hits a certain point, that quadratic is always going to be a positive value. So they're no longer all positive terms, but we can still do the limit comparison test. Because when we do our limit comparison test, we'll now have our limit. If we go through the math, we get 1/4. Notice how I said from n equals 2 to infinity for our limit comparison test. Because we can discard the first term, because if the rest of the term converges, then the rest of the term plus the first term will still converge as well. And then if the rest of the term diverges, then you now have infinity plus a number, which is still going to be infinity anyway. So this is going to be a case of be very, very careful that I am going to do this to you where I'm going to give you a problem where you do have to consider what happens after the first term because the first term doesn't match the conditions for the test that we're going to use. But anyway, 1/n squared converges by a p series, therefore the rule or the series that we want also converges by the limit comparison test. Example number 12. So yes, these are all positive, and yes, this is a decreasing function. So anyway, I look at this n cubed over n to the fourth, which is a 1/n relationship, because I want to know how they change or what's the rate of change. If I do my limit comparison, I end up getting 1/5 for my limit. And since 1/n diverges, then by p series, then the series that we want also diverges by the limit comparison test. And last but not least, I have this problem. So with this problem, I have an n and the square root of n squared. The square root of n squared, if you know, is the absolute value of n. So this is modeling a 1/n squared situation. So that's what I'm going to compare it to. So when I do my comparison, because n is approaching infinity, the absolute value of n is n. So we get a 7n squared over 3n squared, which is just 7/3. Since my limit is a number, I'm now going to say 1/n squared as a series converges because of p series. Therefore, the series that I want also converges by the limit comparison. Hopefully this is very, very helpful for you guys, and I'm signing off. Take care.